Okay, so hello girls and boys. I'm very happy to be here today and to see this lovely audience. The reason is the percentage of ladies here. There was a sociological experiment some time back, which is crossing decades, and this experiment includes children. They were asked to draw a picture of a scientist. And decades back, those children usually drew a picture of a man in a white coat in a laboratory. But nowadays, this has shifted. Nowadays, children, when they are asked to draw a scientist, they draw also girls, maybe 40%. And so the society has really developing towards the better. So I'm happy to be here and to address you today. I would like to first look back at the talks we have heard today as well as yesterday. These talks were about metal clusters. I would like to talk about it because I want you to understand the context of where I'm coming from and why I'm doing the chemistry that I'm doing. So we've heard talk by Sebastian about carbon dioxide, and it's a big issue. And we've heard a talk by Rahul from the University of Manchester about graphenes. And those two talks particularly have something in common, and that's carbon. Because carbon is everywhere. I will speak about boron, but before I start talking about boron, let me say a few words about carbon, which I have started anyway. Yeah. So I'd like to talk about this direct neighbor of carbon, boron, and it used to be once considered a boring element. But these are the big issues. Yeah, if you look around, you can see that everything is made of carbon. You're made of carbon, we're made of carbon. I saw a brilliant talk by Pradeep at IIT Madras about water molecules and how organic molecules, like methane, can be trapped inside clatrates in the interstellar conditions. And that's fantastic. So it's again about carbon. So when I mentioned yesterday, it's really good to give a talk today after our yesterday's discussions, because I have the feeling I know you a little bit better, especially after eagerly listening to your questions which you gave yesterday. And when I mentioned that in chemistry you can make a simple experiment in the laboratory, I'd like to give you an example. There were two young boys, Stanley Miller and Yuri, and they did an experiment which we can, of course, today question to what extent it really speaks about the origin of life. But the experiment which they did was fairly simple. I think you would be able to do the same kind of experiment in your laboratories here, which I had the pleasure to see earlier today, thanks to Pradeep. So this experiment was to imitate some conditions as they might be on the planet in the early days when life was evolving. I don't want to go into too many details of this experiment. I just wanted to show you this one example as something that it often in science is about the thought, the idea. Not so much about, also about experimental equipment, but essential part is the thought, or the train of thoughts that lead to a certain discovery. So you all know these molecules, they are very simple, and the rules in organic chemistry are well established. So you see a single bond, and you say, okay, 2 electrons, 2 centers, so it's a simple single bond. We know all these other molecules, and I'm just giving them here as examples. We've seen we've seen other molecules during previous talks. But now let's look at boron, because one thing which I would like to pass on to you is that you have to think about chemistry and experiments in a broader context. That distinguishes great scientists from scientists who have kind of narrower viewpoint on things. So boron is found on the planet in Turkey and in California, also elsewhere. But these two places are really abundant when it comes to boron. And in what form is boron found? It's in the form of boron oxide, a mineral called borax. Just like when you look at a lecture about gold, silver, and copper, you immediately, by trying to realize in what form you can find these metals in the nature, you can get something about their chemistry. And often, what you see during the talks can be explained in simple terms of that simple chemistry. That gold is inert, that's why we find it in its metalline form, in its metal form, its bulk form. Silver is more reactive, why we all of a sudden start seeing not just silver in its bulk form, but also as minerals, mainly with sulfur. And why we find so many different minerals of copper, where copper is involved in a bond with oxygen. So what's around you is in fact translated into experiments that we are doing and experiments that you see during all these talks. So this is borax, a mineral. Oops, I stopped working. Oh, yeah. Oh, it's here. So it's a white powder, and I need you to remember that because it's almost like sand. So the white fields, I had the pleasure to visit in California to Sealess Valley Minerals. Do you have a different pointer? Because this one really doesn't work too well. Even though I have the software for it, it might be good to have a different one. I know, but it's just simply, yeah, super, I will have to. So this is the place in California, not very far from a place which I almost call my second home, Los Angeles. So Sealess Valley here, and there is a town called Boron, which is here, where they also mine lots of borax. So, but it's about boron and oxygen, a simple molecule. That's one of the reasons why boron 100 years back was thought to be a boring element. Just like imagine what you can do with organic chemistry. You can develop many different molecules, and then you have kitchen salt. What can you do with kitchen salt? It's a simple molecule. And there was one man 100 years back who was interested in whether he can turn boron into something similar as carbon. He was interested if this close proximity, the fact that boron in the periodic table is next to carbon, whether it's really only that boring element or whether it can blossom into something like organic chemistry with the diversity of molecules. And so this was his motivation. His name was Alfred Stock, and I'm not going to read it, but it's interesting to look at the train of thought. He wanted to make molecules out of boron that will be as rich as carbon. So in about 100 years back, more, in 1912, he published the first study on boron hydride. And here are a few examples of these boron hydrides. Diborane is with 4 boron, 5 boron, 10 boron, 12 boron atoms, and he prepared them. And he didn't understand the structure of these molecules because he thought he prepared these molecules and that he prepared something similar to hydrocarbons, where you have methane, ethane, propane. So, in fact, he didn't know the structure, but he was very accurate in his work. So he knew there was B2H6, he knew there was B10H14, and it didn't fit those hydrocarbons that have 10 carbon atoms. So he knew there must be something different, but he didn't have tools to look inside. But he prepared these molecules. Now, let me talk about the history of boron hydride. After the discovery of boron hydride, which was purely the product of his curiosity, these molecules were left out of interest. No one was kind of interested in these molecules. And during the Second World War, and after the Second World War especially, scientists have realized that when you burn these molecules, you release a lot more energy than when you burn hydrocarbons. And all of a sudden, people started thinking, what about if we use them as rocket fuels? And this was a really big impulse. I have to say, unfortunately, when it includes military purposes, I'm never that happy, but it really brought lots of money into this research. And that's roughly the time when the Institute of Inorganic Chemistry, former Institute of Special Inorganic Syntheses, where I'm from, was established to look at hydrides of light elements, especially boron, as materials that have this use, to investigate these molecules and to prepare them, to investigate pathways, chemical pathways that might lead to technological production of these materials. So these two people who you see here were my predecessors at the Institute. They were the establishing fathers of the Czech boron group, and they organized in 1971 an international conference on boron hydrides, and this conference was attended by stars, scientific stars such as William Lipscomb, Robert Williams, Frederick Hawthorne, or Herbert Brown. Those two, Lipscomb and Brown, later on in the 70s, both got Nobel Prizes for, in case of Lipscomb, for his contribution to understanding the structures of these molecules, and Herbert Brown for his contribution for the use of boron hydrides in organic chemistry. So, yeah, they sent this memorial placard to the Institute, and I had the pleasure to have Professor Pradeep at our Institute, so I took a picture of him next to this placard. So maybe within a decade, Professor Pradeep will extend the number of people who visited to the Czech Republic and who later were rewarded with the highest possible prize. Okay, so now I would like to show you how diverse boron clusters are these days. We categorize them. It represents a chapter of advanced inorganic chemistry in the university textbooks. So we have closed systems, nido systems, arachno systems, depending on how closed or open these structures are. And because there are so many of them, and this itself would give for a series of talks, I would like to focus only on one, because in addition to giving you this introduction, I would also be happy to show you what brought us together and why I'm here today. So I'd like to focus only on this molecule that is at the bottom, which is the most symmetrical molecule, and it exists as this dianionic species. I need to ask you, because I know there are many undergraduate students as well here. These lines, they're not bonds. You should not be looking at these molecules, at these polyhedral molecules, as you look at organic molecules, whereas where a line is a bond. In this case, it's a triangular phase. So we talk about so-called two-electron three-centered bonds. And this is a concept which was in 1940-something established at the University of Cambridge by Longett-Higgins. And Longett-Higgins was also the person who provided the first insight. I've been often wondering why it wasn't him who got also a Nobel Prize together with William Lipscomb. But such is life. There are many excellent scientists who have never got Nobel Prizes, although we might think they would deserve it. So, and he came with this concept. He explained the structure of diborane, this B2H6, and so he proposed it. So it was a fantastic work. So please, when you look at it, this is the kind of bond here on this triangular face is a bond. So now if you can do lots of diverse things with these molecules. You can replace two BH vertices. Oh, the reason why I'm drawing them sometimes green is that when you burn boron hydride or even ester of boric acid, the flame is green. It's a nice green color. So sometimes if you look at the film about James Bond and you see green flame, it's often coming from boron. Okay, so we can replace for the isolobal CH vertice, we get this neutral molecule, and this neutral molecule, which we call carborane, exists as these three isomers. You can see the carbon atoms being either in adjacent positions or a little bit further, or in the antipodal positions. And that somehow influences also the properties of these molecules, because this is a strong dipole, this is no dipole. So we have been interested in putting these molecules on the surfaces. And that's when we sort of looked and prepared a portfolio of molecules to which I will get a little bit later. Here you see two examples of these molecules. We can selectively attach thiol groups. And I've talked about how silver particularly is, I mentioned it briefly, how silver really likes to make bonds to sulfur. That's why if you look at the column and you look at copper, silver, and gold, why silver is found with, as minerals with sulfur. So it likes, not so much gold, but it has affinity to sulfur as well. So we've prepared these sulfurous groups and attached these molecules on a flat gold surface, as you can see it here. So we can have these molecules that have practically identical steric requirements, which means the geometry of these molecules is the same. Of course, we are often presenting these pictures in a static way. It's better to look at it. But these molecules have their breathing vibrations. So especially at room temperature, everything is kind of shivering. And when you have them on a surface, the structure doesn't really manifest itself, the fact that there are subtleties in the symmetry of these molecules. So they behave like solid spheres. And I'll show you now some chemistry of these molecules, which has been done with a friend of mine, Paul Weiss from UCLA, and we've looked at these molecules using scanning tunneling microscope. We found that these molecules can be sort of standing on the surface either with both legs as dithiolates, which means that both SH groups lose the proton, or one of it is sort of lifted up. And this affects the stability, how when you desorb the molecules, and so on and so forth. And of course, we didn't see the molecules that are attached this way as monovalent with this as keeping the hydrogen atom. The hydrogen atoms on these pictures are just omitted for clarity, so I'm commenting on it in more detail. So there's hydrogen, and so we see them protruding from the surface, while this isomer was practically pristine. You don't see any protrusions. And we identified all the molecules to being in this binding mode, while here there was a fraction of these molecules, bound this way and this way, two fractions. And so we thought, why? And now I'll go back to the very simple chemistry, which everyone, in fact, understands. I was showing this at IIT Madras, and I was happy to see in the audience Dick Zayer from Stanford, and particularly when I was mentioning how simple chemistry is behind this observation, I was happy to see him nodding, because it was clear to him that these molecules, this is a picture, as you can see, this is quite an old picture, so it's the acidity which stands behind it. So you can see just the percentage. So this is an expression with a few numbers. You see that under neutral conditions, when we absorb these molecules on a gold surface, we get 20% of these molecules being bound in this monovalent form, and 80% as dithiolates. In this case, almost 100% of molecules bound in this monovalent way, where the other SH group keeps the proton. So there's a big difference between these two isomers, one here and one here. And the difference is in the acidity. Because you can see I went on this slide to monothiolate it just for the simplicity of it. Yeah, if you have two SH groups, it's a dibasic acid. So I want to comment on these monothiolated isomers. And you see that if it is attached to boron, the pKa of the SH group is 10. If it's attached to carbon, the pKa is 3.3. So it's a huge difference. And of course, depending on how much this isomer or that isomer wants to lose the proton from the SH group, then it shows bigger tendency to be adsorbed on a gold surface either as a thiolate or only weakly physisorbed as a thiol. So through the adjustment of pH, we can manipulate this anchoring group on the surface. So that's an interesting and good tool for structuring the surface, for desorbing, for example, molecules, and to reducing the concentration of molecules from the surface. Okay, I've got to quite a few isomers, right? All these are isomers. It's made just like a schematic to better show you where the carbon atoms are. Otherwise, carbon and boron atoms are practically indistinguishable. The size of these two atoms is very similar. So we have these rows of isomers. Okay, if you attach one functional group, whichever it is, to this cage, you get 5 isomers. Here, you get 5 isomers. Here, you get 2 isomers, because these boron atoms and these boron atoms are identical. So you have in total 12 isomers of the monothiolated derivatives. You have plenty of isomers if you have these dithiolated. So we have prepared many of these isomers always for a particular reason, to understand the assembly, the self-assembled monolayers on flat surfaces. I'll play a 1-minute video to show you. Yeah, it's coming. To show you this message. In fact, the video delivers the same message twice, using 2 different systems. I'll comment on it. We'll be using the molecules on self-assembled monolayers. They represent artificial blocks. There's a free rotation about the sulfur vertex bond, so the molecule can also rotate. That contributes to its behavior on the surface, that it behaves like a solid sphere. And so you have, here's just a first pair of isomers with one SH group. It's always orientated downwards so that you see also the differences in the dipole moment. And you see those pairs that were presented here are members of large series of isomers. So we haven't, of course, prepared all those isomers, just some of them. And now, this will show you what I've talked about. That we can, to some extent, look at these molecules as solid spheres that can put on different colors, depending on which isomer that particular molecule is. So we can be one isomer, and we can make complicated patterns on the surface. without, and that's important, without changing the geometrical pattern. That's like a dream of a physicist, to have a molecule and to put here whichever atom of whichever element, then to put it here. Often the discussion between a physicist and a chemist is complicated because chemists have certain limitations. They need to understand the way how to prepare these molecules. So it's a little bit tricky. And here we have geometrical pattern in which we can replace different isomers and keep the pattern identical, and therefore only focus on changes that are installed within the pattern by different molecules of the same steric requirements. Okay, here is the, I would like to say a few more words about this molecule. We can investigate it in ultra-high vacuum. Of course, maybe that's something you cannot do here because you need, for this investigation, you need scanning tunneling microscope for UHV, for ultra-high vacuum. Why did we do it? We wanted to know how the molecules grow on the surface, and trust me, this is work which takes time. So it's really good to have a student who fully focuses on the device and on STM, and who really plays with these molecules, who put some passion into it, and then we can get really good data. So it tells us information and how the molecules look, how they arrange on the surface. You can see we see them, of course, as just like simple dots. But I've been talking about these carboranes and closed carboranes. I would like to go further and to show you that we can also, not to make it too boring, not to talk just about one or two molecules for the whole time, I want to show you what further things we can do with these molecules. We thought it would be good fun to introduce further functional groups and to open these closed systems to some chemistry on the surface. So we've made, and you will see, I would like to recommend to see a talk by Indranath. So he will talk about clusters, and the effect that ligands can have on luminescent properties of these copper clusters. So I'm myself forward-looking, if it's today, to see it. So this is about all these molecules, and I will quickly go through to here. Oh, sorry. So here you see further molecules derived. Again, it's about isomerization. It's about isomers. And so because it's the world of isomers which makes the chemistry advantages. I wouldn't work with boron if I didn't find it interesting. I have seen talks by others, sometimes started with, I work with this chemistry because simply I love this molecule. That's not my case. I need to see the rational aspect behind it. So that's why I'm talking about it. I'm also often asking myself, is it worth doing this experiment? Is it not? And I want to see the potential impact. And in the case of these molecules, I do see the impact into many fields, into the area of metal clusters which together Pradeep and I are developing. And I'll get to that. Okay, so I've talked about this carborane and what we can do, how we can derivatize it. But now, it's maybe time to go further. With a friend of mine, Jonathan Bold, we've looked at these metal dimetallics. So because the two vertices doesn't have to be only carbon atoms, but also metal atoms. And these, all of a sudden, these molecules bring another feature. And they can uptake small gas molecules, such as oxygen, carbon monoxide, sulfur dioxide. So, and of course, these are coordinated the metal-metal vector. So you see just the manifestation of how it looks in the NMR, which is maybe not so direct information for you as, yeah, we can also control. I'll get to the picture with the colors. So you see the UV-vis spectrum here for example, the diplatinum carborane with 2 platinum atoms and 2 platinum atoms with oxygen. And you see you can easily control the release of oxygen and uptake, and can do many cycles, infinite number of cycles. These are very stable molecules. So all of a sudden, we have a molecule which we could potentially put on a surface, and on the surface of either a flat film or a cluster, we could be playing with the uptake and release of these oxygen. And so it's getting us closer to complicated systems that work in nature, like photosynthesis and so on and so forth. So this is how it looks. When you just take the molecule, this is the top view of the space-filling projection of the molecule. So you see there's like a little cavity in between those ligands that are attached to the metal atoms. This is with oxygen, without oxygen. This one is with SO2. And you see they change color if you have them in the solution. So this is, I'm presenting it to give you the idea of how diverse system we have in our hands. Okay, how about if we completely remove the carbon atoms and if we have it like an open phase? It will have, and we thiolate it to be able to anchor it to the surface. Okay, we will have an open phase that has its own reactivity. So it can trap a metal atom, and we can go further to catalysis. So we can have these atoms with palladium here. We can heat it up, get rid of these phosphines, for example, that are weakly bound, and have a very reactive metal atom stabilized inside the borane cage. 4 minutes. This is where we met, Pradeep and I, at a conference in Kauai, and we started our collaboration in 2018. So I see a bright future of this area that merges boron and metal clusters. So this is just one of the most recent examples by Arijit, who is now working at Karlsruhe Institute of Technology. He is a student of Pradeep's, and he prepared this cluster. And the reason why I'm showing it relates to what I said at the beginning, the corrosion of silver, In fact, in this cluster, we see the metal core, we see sulfur metal shell, and then we see the ligands on the surface. And if you look at corrosion, which means silver film which gets corroded, it's difficult to see it with atomic precision. Here, this is a cluster that represents all 3 types of materials: metal center, metal sulfide, and the monolayer that stabilizes the whole cluster and that allows us to look at what it looks inside. Okay, very quick information, because I mentioned Rahul and his interest and passion for graphene and for these materials. We've been interested in that as well. So with Andrei Turchanin from the University in Jena, we have cross-linked the molecules, and we've got to these self-standing membranes. And if we remove the hydrogen further from these membranes, we'll be very close to borophene. Now imagine you do not use carboranes, but you use phosphoboranes, azaboranes. You name the element of the periodic table, you put it on the surface, we cross-link, and we have a layer that has perfect homogeneous composition, over 1 centimeter. Okay, just some further prospects, because I want to also show you different geometries. I've talked about these molecules. This particularly is derived from a bicapped pentagonal antiprism. But there can be also tetragonal antiprism. We can play with rod-like molecules. I've briefly mentioned these open faces. We can adjust the bottom of the molecules by various other atoms to install local dipoles and get further insight into these molecules. Okay, that's for now almost all. These are my collaborators from UCLA, Paul Weiss, Anastasia, Alex Spokojny, Pradeep from IIT Madras, Michal Dušek-Pavelínek from the Institute of Physics of the Czech Academy of Sciences, and Andrei Turchanin from the University of Jena. I'm happy whenever students from India come over to Prague, because I think it's a super enrichment. I've never had a visitor who would be a girl. It was always Suraj, Arijit, Vivek, Deepak. I would next time, it must be girl, 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 to make it equal. So yeah, and just some, this is what it looks like. At my place, we still have 55 seconds, I'm perfect on time. So this is what it looks like, and I had the pleasure to have Professor Pradeep in Prague. We sometimes organize for friends like a small gathering with a scientific talk. And so this is what we did with Paul and Pradeep. And I would like to finish my talk by showing you Pradeep, by showing you Professor Pradeep in a different way than you know him. Thank you very much for your attention.
Thank you, Professor Bates. Now we can have few questions.
Yeah.
How do you your boron clusters are interesting. How do you deposit them on the surface to study AFM or STM?
Okay, we've used multiple ways. First is very easy. Because all these materials are solids or crystalline solids that are easily soluble in organic solvents such as ethanol, chloroform, dichloromethane. So you dissolve them and then you take the metal substrate and you immerse it. That's from a solution. You take it out after some time, you wash off the excess of the material with pure solvent, and you have the monolayer. This is an easy technique. Of course, the easier usually the technique is, the more difficult it is to get information from what's going on the surface. But this is one. Another one it was from gas phase, because most of these molecules that are presented sublime. So if you heat them, you can also use sublimation as a purification method. So you can also generate certain tension and deposit them from gas phase.
But you have to keep the surface clean.
Yes, we have been
How
using...
do you do that?
In case of gold, we have been using surfaces that were flame annealed freshly before experiment with hydrogen flame. This is standard. In ultra-high vacuum, it's of course complicated technique, or complicated. It's you scatter the surface to get rid of any impurities. Then you anneal the surface, which means you heat it up. You scatter the surface, you anneal it, until you achieve surface that is really nicely crystalline. Yeah.
So the orientation will be different depending on the plane that you are exposing. That probably...
This leads to differences. You're absolutely right. In case of the gas phase, we can easier achieve sparsely covered surfaces, especially if we want to know how the monolayers grow, if we want to have this information about sparsely covered surfaces. I would like to tell you a story about questions. There are two sayings, if you ever hesitate to ask a question. One says, there are no stupid questions, only stupid answers. And the other one says that the most stupid questions are often laid by the cleverest students. Whichever way you want to look at it, it aims at supporting you to ask questions.
Okay.
Yeah.
Thank you. One question from student.
Oh, sorry.
You have talked about self-assembled monolayers, and in boron molecules, when you introduce like a mercaptor group, SH group, do they make a good linker when you take gold plates? Do they make better linkers if it's sulfur linkage?
Yes, it's a very good question. They make a very strong bond to the surface. To demonstrate that, we've done several experiments. Because your question targets kind of bottleneck of the system. So we've been investigating different of those bonds. Bond between the vertex and sulfur, the bond between the sulfur and the metal. If we expose them to heat on a flat surface, these molecules survive in the form of a monolayer very high temperatures, 400 degrees Celsius. So it's a very high temperature. If we use a bit more complicated techniques such as TOF-SIMS, which is secondary ion mass spectroscopy, spectrometry, so then we sort of sputter the surface and we sputter the molecules off. What first breaks is the bond between metal atoms and other metal atoms, rather than the bond between the surface metal atom. That shows you the strength of the whole system. So it really is extremely stable when we force the molecule to adsorb as a thiolate, sulfur-silver bond. If we have the molecule only physisorbed, which means without the SH scission, then of course they are more labile and we can desorb them.
And if you introduce metals, you talked about metalloboranes. If you introduce metals into this molecule, do they make good conductors if you trap them between gold plates?
That's also a very good question. You're right. Those molecules, when we put a metal atom inside the cage, are metalloboranes. But when you speak about a conductor, I always kind of struggle, because electrical conductivity, that's something we usually perceive as a property of bulk material. So you have a wire, copper wire, gold wire, you have some rope, and you can measure the conductivity. When you go to conductivity of something which is a molecule, you can also ask yourself a question, what do you mean by conductivity? So there is, what we can measure is, of course, some sort of STM current voltage curve, which of course looks completely different than any curve.
Maybe an IV curve. Or...
Yeah, that's what I mean. How do you make a contact to one molecule? Through a tip. The tip is usually defined. So what you see is kind of the conductivity of the molecule, because the electrons skip through the unoccupied orbitals of the molecule. So we do see them, because they are small, they do not form an insulating layer. I can't really answer the question whether it's a conductor, good conductor, because conductivity is something that I perceive as a property of bulk material.